Hi students, welcome to HSC Earth and Environmental Science and Module 7 on Climate Science. This is video number 10. We're going to have a look at recent climate variation and ice cores. So what we want to be able to do is identify and explain more recent evidence of climate variation, including but not limited to ice cores containing gas bubbles and oxygen isotopes. So what's recent? Well, recent is a very relative term. Recent for me could mean what I had for breakfast this morning. But recent for geologists are much longer time frames and can mean anything from the last few thousand to 100,000 to 10 to 15 million years. Don't forget, what we're trying to do is we're trying to contextualize what we know about recent history in the context of a 4.5 billion year old Earth. So this is a planet which has got a very long history, and sometimes what we're trying to do is just to pick out a tiny little portion of that history. But up till now, we've had a little bit of a look at some of the areas of evidence and some of the cycles that have contributed to changes in the climate over the millennia, and in fact over much longer periods of time than that. So it's enabled us to try and gather in a little bit of a history of our planet, of the fact that there are some cycles that continue and that reveal patterns of highs and lows, certainly around carbon dioxide levels and the amount of the Earth that's receiving radiation from the sun, the albedo effect, the movement of the continents and the supercycle effect, and how the distribution of the oceans can also contribute significantly to matters of climate, and the fact that the climate itself seems to have cycled between greenhouse conditions and icehouse conditions. So it's time to move forward. It's time to have a little bit of a look at the most recent periods of time that we can look at. And so somewhere in the last few million years is what we're trying to do now, to see if we can hone our techniques a little and see if there's any areas of evidence where we might be able to start looking back a little beyond our own lifespans. So what we want to try and do now is we want to go back a few thousand years, back to the last couple of million, to see if there's any indication of cycling that's happening or that has happened in the past, what sort of things we can do to try and get a handle on the nature of these cycles, and of course when we compare them to what's happening today, whether these cycles are just consistent patterns that have continued through in today, or if there's any differences. So we're going to look at a number of different areas of evidence that have provided data about these sorts of issues, and one of the first ones that we want to look at are ice cores. Particularly in the areas around the North Pole, up around Greenland, and the South Pole in the Antarctic, ice cores have allowed climate scientists to gather lots of data about global temperatures, and they do that from gas bubbles that are stored within the ice that get released when the ice basically is being examined, and also from what we've talked about before, the isotope, the oxygen isotope data. So that delta 18O value, which we talked about in a previous video, that's one of the important things that we can gain from our study of ice cores. The idea is that the ancient climate, or at least the ancient atmosphere, gets trapped in ice bubbles, and then if we can take sections of the ice, we can get an idea from the depth. There's a correlation with age, and we can get a sense of what sort of materials were in ice of different ages. Now that might sound a little bit hit and miss to you, and in some ways it is, and one of the reasons that one of the things that we associate with our ice cores is some areas for correlation. So often what we want to try and do is we want to correlate or see if there's some level of agreement between information we get from one source and information we get from another source. Volcanic dust is a really good type of associative data that we can look at. If we find dust particles that have maybe been released from an explosive volcanic eruption, and these have made their way into the atmosphere, they've fallen maybe with the snow, been buried in the ice, and now there's a layer of those, and we can again look at things like radiometric dating techniques to get a more focused idea of exactly what sort of age the ice is just below and above these little fragments, and obviously that formed at about the same time. So it's very important that we cross-reference what information we have from our ice cores with some of the historical events, particularly historical volcanic eruptions, to see if we can create some correlation between these. And when we do, we find that there's a high level of accuracy associated with our understanding of ages based on these ice cores. So what are we going to extract from our ice cores? Well, one of the things that we're going to extract is our oxygen 18 data, and we're going to build these delta 18O curves that we talked about previously. In addition to the oxygen 18, there's also an isotope of hydrogen called deuterium, which is H2. And H2 is basically one proton and one neutron in the nucleus of the hydrogen atom. It's a heavier form of hydrogen, and it's referred to as deuterium. So sometimes you will see the delta D value, which is just this change in deuterium. So again, we're talking about ratios of uncommon isotopes like deuterium compared to the more common natural isotope, which would be hydrogen 1. In the same way that we looked at oxygen 16, the naturally occurring and very abundant isotope of oxygen, against the oxygen 18 levels. Our context for this is that snow falls on inland ice sheets in both the north and the south polar regions, and they contain information about what was happening at the time, ambient climate, which can go back for hundreds of thousands of years. And these tiny air bubbles that are trapped in the ice have allowed us to study the composition of the atmosphere at that particular time, and as we go through the ice core, to look at different periods of time to see if there's any changes in any of these levels. Because we've linked the delta 18 oxygen levels to temperature dependence, we know that as the levels change, so they indicate slight differences in the global temperatures, or at least the temperatures are in that region around that time. And so when we analyze snow on the glaciers, we can create some sort of a timeline that shows how the temperatures have varied for that particular area. And as we increase our understanding and increase our sample size obviously very important in the scientific process, and as we continue to increase our sample size, we start to get more confidence in the type of data that we can extract from these very important sources. As I mentioned, accuracy of the data is very important, and being able to put specific dates on specific parts of the ice cores is again a very important component of this. So we're always looking for ways to correlate the data that we have from one source against other sources and see if they help to confirm what it is that we think we know. So some of the things that we use in association with ice cores could be things like horizons, that are layers formed in conjunction with historic events like the volcanic eruptions I talked about previously, the buildup of particular types of particles, or even just the deposition of particles that maybe have come from different events that may contain some important elements that maybe display some level of radioactivity and allow us to use that sort of radioactive dating techniques that we've also talked about earlier in this course. So ice cores are just one source. We've talked a little bit about ice cores in the past and what information we get from them, and there's some really good activities that we're going to be having a look at in class that'll help us hopefully to understand the data we extract from ice cores in a little bit more detail. Thanks for watching.